All right, we got my newest PCBs from JCPCB delivered. So yeah, let's take a look and see what we got. Ooh, there we go. Nice. Those are sweet. Sweet. So these are a V2 of my little power supply boards. So they're a little bit bigger than the old ones, and they've got a bunch more components on them. They're a little bit more complicated. So yeah, that's what we're gonna look at today. We're going to test these guys out, make sure that they actually work first of all, and then I can step through the change in the designs and explain to you guys what I did and what the difference is. Basic differences, I've swapped out using linear voltage regulators with using switched voltage regulators. The two big components you can see in here are these inductors, which are needed for the circuit that the switched voltage regulators use. So they're those big new components. So board's a little bit bigger than the old one to accommodate the new components. Everything else is the same. Switching circuit's the same. Just need to solder on the switch and the header pins, and then yeah, can give this guy a test. Footprint is also a little bit bigger than the old ones, but not by much. So that's pretty cool. So yeah, let's next step. We're gonna wire up some pins and some switches, and then test this guy out. And you guys can follow along.
This video is sponsored by JCPCB. More about them later.
Alright, before I solder up this new board to do a little bit of testing, I decided to give a little close-up look of a side-by-side of the new and the old ones. So this is the old one here. This is the new one. You can see the new one is a little bit bigger, not hugely bigger, but it is a small bit bigger in terms of footprint. But it also has more pins on it, you notice. So another key difference that I mentioned earlier is that the linear voltage regulators, that's these guys, are gone on the new design, and now I use these tiny little switched regulators. And the other difference here is that we actually have a different pin out. So the pins, it does the same thing. So it's got there's ground, V in, and that there's 5 volts and 3.3 volts. But what the old one didn't do was the old one didn't give a switched version of the input power as an output. So that meant that if you wanted to use this, if you wanted, say, if you're putting 12 volts into this and you wanted to use 12 volts somewhere else in your circuit, you had to just tie that to V in, and that meant that it wouldn't actually be switched. This one has an output here, which is just called V out, which is actually just directly tied to V in, but through the switching circuit so that you can turn on and off, and you'll get some switched on and off 12 volts or whatever input voltage you want. So that's just a little bit about the differences between the two boards. I will go over to the computer in a while, and I'll kind of do a little deep dive into the difference between these linear regulators and these switched regulators, and what all the rest of the circuitry that's involved in setting up the switched regulators, because it's a little bit more complicated, not wildly complicated, but they just work a bit differently. So we'll talk about them and talk about the differences and the advantages using the switched over the linear ones. But I got to make sure this works first before I go spouting off about them. So let's get a solder this up and test that, and then that'll be next. All right, there's the job done. Ready to test. I'm so nervous about this part. All right, let's wire it up and test it out. See what we get. So we have a little bit of a problem here. It is working. Doesn't blow up when you flick the switch, which is that's always a good sign. But the voltages aren't quite right. So my V in is fine. I've set this to about 7 volts in, so that's cool. Ground, yep, that's cool. And then I've got the 3 switched voltages here, which are all 0 because it's switched off, which is what it should be. But the problem comes when I switch it on. So when I switch it on, the V out should match V in, which it will. And then we should have 5 volts and we should have 3.3 volts, but unfortunately we don't. So if I switch it on, we get our power light comes on, and then I can check all my other voltages. Yeah, ground, fine. V in, yep. V out, yep. Don't really expect. Then 5 volts, yep, thereabouts. And then the 3.3 volts, unfortunately, that is not right. So yeah, we got a problem there. I checked around the board just to see if it's short or something. I don't think it is. So I think I have done something wrong with these 2 inductors. So the way these little voltage regulators work, I'll go on the computer, I'll show the circuit diagram in a little bit, but basically you set up a little feedback circuit in here, of which the inductors are part of them. Now, what I was reading in the data sheet was that the only thing that you had to do different was 2 different inductor values. The difference between setting it up to 5 volts or 3.3 volts was 2 different inductor values. I'm suspecting that I may have made a mistake there, and maybe there's actually more involved in doing that. So I'm going to investigate that. I'm confident that one of them is working at least. I'm getting that approximate 5 volts out of one of these, so that's pretty good. But the other one, obviously, there's a problem. So these aren't useless, the boards. I'm just going to mark these boards, scribble out the 3.3 volts with marker, so I know that they're actually just 5 volt regulators. They don't do 3.3 volts, these ones, which is fine. We'll switch to 5 volt regulators, fine, whatever. But yeah, that's a little bit irritating. So I will go and check and see if I can figure out what's going on. And yeah, I'll talk you guys through the overall of how these work as well, and then we'll see if we can, if I have a deep dive on the data sheets and see if I made some mistake and figure it out. So let's do that next, and then we'll come back.
JCPCB is a modern PCB manufacturing and assembly service. I've been using JCPCB for a while now, and honestly, I've been really impressed with it. Their manufacturing and assembly times are really fast, and so is their shipping. The last PCBs I got manufactured, assembled, and shipped to Ireland from China in a week. One of their features that I love is their built-in parts library. You can search and spec out parts before you select them, and you can know before you order if your parts are in stock or not. It's really useful, and I use it all the time. JCPCB now offers 6-layer PCB manufacturing. Check out the link in the description for a $30 coupon to use off your first order of a 6-layer PCB. Thanks to JCPCB for sponsoring this video. Don't forget to check out the link in the description to avail of their fantastic services. Okay, so let's talk a little bit about the new circuit that we're using to do our voltage regulation. So this is my new circuit that's set up here. It's the same more or less as the old one. The switching circuit didn't change at all. The part that did change is all over this side of the circuit. So you'll remember, or you may not remember, but I'll throw a little picture somewhere, you'll see it, what the old one looked like. But basically this right half of this entire circuit was really much simpler. There was a single component here, and then they had the outputs. And what those single components were devices that are called linear voltage regulators, or low dropout voltage regulators, and they're not great. Or they have a purpose, and they work reasonably well at what they do, but they do have some fairly serious drawbacks that make them not ideal for a lot of applications. So one of the key things about them is the way in which they regulate voltage is essentially by dispersing it as heat, more or less. So the low dropout thing is like you don't want to be feeding them much higher than what the output voltage is meant to be. So for example, if you have one of these voltage regulators and it's a 5 volt regulator, and you give it maybe something like 7 volts, it'll regulate down the 7 volts to 5 volts and do a pretty good job of it. But it will effectively just drop all of those 2 volts of difference potential in energy out as heat, which isn't a huge amount if it's only like 2, But you may run into a problem then, say if you were to put 12 volts into a 3.3 volt regulator. That's obviously wouldn't be great. So then you're trying to step down a much higher voltage, and you're releasing a ton more heat, and your components could just burn out. And also it's just a waste of energy. So you're basically just putting energy into heating up the air around it for no good reason. So this came as a suggestion when I first built this. The first version of this, the V1 of this, was to use a switched regulator, which is what I've gone with. The actual regulator itself that I'm using was suggested. The specific one that I've ended up using was actually suggested by a comment on the last video. So I'll throw a little screenshot up here of that. So thank you very much for your suggestion. And yeah, I've done it and it works. So thank you very much. And also, yeah, definitely a big difference in the heat dispersal. So anyway, with that said, let's look at the new components. So this is the new switched regulator. So there's two of them here. You notice they're basically identical layouts. One is set up to give me 5 volts out, and the other one's set up to give me 3.3 volts out. They both take the same input, so the output of the switching circuit goes in as the V in to these guys. And then there's a bunch of other stuff that goes on here, which I don't want to go into in huge detail, but effectively the way they work is you put in some input voltage, and then you have this like feedback loop set in here with some external components. You can tune the output voltage by modifying what components are in this feedback loop. Very critically, there's a couple of different things that are quite critical to these type of buck converters. This relationship between this voltage divider here and the inductance as well is quite important. There's a few capacitors in here which have different jobs, and they do make a difference, but the key component differences are the inductors and these two resistances. So yeah, that's about it really. You set up the correct circuit here, which you can find in the datasheet for the parts, and you set up the correct values, which I'll get to in a second, but you can also find that in the datasheet for the parts for a bunch of common voltage ranges. And yeah, this the little regulator chip turns on, takes the input voltage. With this feedback, it then sets the output voltage to be something like what you want. And these are quite good. There are some trade-offs with them. They're not like a perfectly stable voltage. They can have some ripple in them because they're based on like a switching system which turns on and off effectively the voltage to give you this like regulated output. You can think of it as something like the way if you have an Arduino or something and you have a PWM signal, you could bang a bunch of capacitors in line with it and you can make a varying output voltage, but you'll see some ripple in it. Something similar to that, but more complicated and obviously better than that is going on in here. And then this feedback system is what sets what the output voltage should actually be. So it's like some output capacitors here and stuff which are meant to reduce that ripple. But yeah, I'm not going too deep into them. I'm not very au fait with the inner workings of them, but that's my rough understanding about how they work. So last thing I want to show is I'll just talk through the datasheet a little bit because it's actually super useful for this component, and I can highlight how I made the mistake that I made in setting my values. So I have two inductors in here, L1 and L2, which are different inductors, and they have different values. One is I think 5.6 and one is 4.7. And my mistake was assuming that those two inductors were the only differences you had to make between the two circuits to get the different output voltages, but they're actually not. The difference is actually these resistors as well as the inductor. So I'll show you where you can find that. But anyway, let's have a look at the datasheet. So yeah, you can read through this if you so please. Lots of really great details in here about how it works and stuff. But the main parts that I needed were to know how to implement it. So they give you this lovely little circuit diagram, which I basically copied to put into my voltage regulator implementation, and it worked fine. And this is actually where I can point out to where I got confused or I made an assumption which was wrong. So this circuit diagram you see here, it shows all those stuff and it gives you some component values. Then there's this graph underneath which gives you some output values here. So I read this and I saw a V out of 5, and then I read this one, I saw a V out of 3.3, and I went, oh cool, they're the two values that I need. And it highlighted these inductance values here, the different inductance values. So I kind of assumed that those were the values that I needed. Turns out that's not the only difference. So I kind of made a complete assumption here that the rest of this all was all the same, and it was just the inductors that needed to be different. So a bit of a complete assumption, and turned out to be wrong. That is a difference between getting 5 volts and 3.3 volts, but it's not the only difference. So if you scroll down, you can see where I would have actually found that information. So this table here, conveniently labeled setting the output voltage, gives you this formula that you can use to figure out how you should set the output voltage. And it also gives you this then handy dandy table of all of the components and what their values should be for some typical output voltages. So you got 5 volts and 3.3 volts. And you can see most of the components are the same. We have the 2 different inductance values here. And then we've got the one of the resistors and then another resistor that's different. And that's the key. So basically, for my mistake, I have to replace one of these resistors, and that's it. That should be the main thing. There's a capacitor different here, which I will change as well, but yeah, it's a very, very small difference in capacitance there. Not sure if that would make actually that much of a difference. I'm not sure exactly what that capacitor is doing in the circuit, but I'll probably change it anyway. But the key difference is this resistance value. That's really it. If you want to spec this thing out fully customizably yourself, you can plug in your values here. You can go and figure out your inductance value here and work all this stuff out. One thing that is generally done with these kind of data sheets is the component values that are for common voltages are usually commonly available component values. So you could do something with this and end up working out a set of values that you can't buy the resistors or capacitors for or the inductors for. So that's something to watch out if you're doing this yourself. But generally, unless you're doing something very specific, you're probably going to just need one of these common voltages, and a common set of these components should do the job. So yeah, that's kind of it. Yeah, that's all I really wanted to show with this. Not diving into any huge detail here. One thing I do actually want to point out, another thing, final thing, this data sheet's actually really good. It's got loads of stuff in it. If I read it properly, it would be even better first go around. But one of the things I loved in this was this diagram that they give here, which is just really nice. It basically is telling you, if you're putting this on a PCB, this is how you should lay out your components to get the best performance, which is really, really cool. There's a few of these like traces that actually make quite a bit of difference, like the distance between them, particularly in like the switch, this SW, the length of this trace, and some of the feedback traces as well. If they're longer or shorter, they can actually affect how the converter works. So by laying the components out in this arrangement, you'll get the best performance pretty much, which is really cool to see. Really, really like this guidance to be able to do this, which I then used in my board design. Didn't do it exactly as they did. It's quite hard to see there, but if I go to the 3D version, yeah, you can see it a bit clearer. There's our chip, there's our inductor, and then a layout of the capacitors and resistors as kind of shown in their diagram. It's not perfect. It's not doesn't exactly match. Obviously, your real life constraint by the physical space you have and the size of the components. So these are the inductors I found, and they're quite chunky boys. They're much bigger than you might expect. So when you look at this, I don't know where they're finding a little inductor that's nearly almost the exact same size as the chip itself. I don't know. I went looking, I didn't find any that I could get easily. So yeah, maybe there are a bunch of smaller inductors and I just missed them. But I think commonly they're generally a fairly large-ish component on boards. So yeah, you gotta take that into account when trying to lay out your own board. So yeah, that's it. That's all I wanted to talk about. Next thing is I identified exactly what I need to fix here. I have that fixed, and I am waiting for my new boards to arrive to test them out. So yeah, we'll test out the new boards when they arrive, and then that's going to be it for this. So fingers crossed that all works and that I haven't just spoken loads of nonsense in the last few minutes. Pretty sure I haven't, but yeah, let's let's wait and see what happens.
Okay, so by the magic of editing, we have our new boards, replacement boards made with the resistors swapped, and we can check 5 volts and 3.3 volts, and see if they now give us what we expect. So we turn it on, lights on, always a good sign. And then check our 5 volts. Looks like 5 volts to me. And then we check our 3.3 volts. And yeah, that's 3.3 volts. So nice. That seems to work. Everything else I think is working as it was before. Yeah, 6.95 in, V out 6.95, and ground is ground. Oh, not quite ground apparently, but oh well, that's also not 0. So who knows? Let's not trust this thing. But yeah, it seems to give us 3.3 volts and 5 volts, which is exactly what we needed out of it. So nice one. That works pretty well. Happy days.
So that's about it for this project. Really happy with how it turned out. The boards look fantastic, they work great, and I learned a little bit doing it. So I hope you guys enjoyed it, and as always, thank you for watching, and I'll see you in the next one.